Pembroke. I was at the CCMC for about 6 years, and then I went freelance, and then I'm now at Predictive Science, technically in San Diego, but physically in Houston, Texas. And so the Komodo project sort of started at the CCMC as a way to kind of meant to be not a drop-in replacement, but to sort of provide a means to access the models that are hosted at the CCMC at NASA. And so we had been using Chameleon software, and we wanted to kind of try something new that would scale more easily to plug into all of the different projects out there. So it sort of became a Python-focused project in that it plugs into other Python tools from PyHC. So basically, it's a functional kind of approach. And so the goal is to sort of simplify the access to these models in a way that allows scientists to easily work with models and simulation data, but also observational data, and also just pure math or things that might come out of, say, Plasma Pi. I believe we have the Plasma Pi representative here. So, and I think, I'm not sure if everyone is here. Is Rebecca and Lutz are also, are they not? Oh, Rebecca. Okay. And Lutz might be here, but so
yeah,
Rebecca
too.
Okay. Rebecca's done some great stuff with the Plasma Pi interface for Komodo. And then I've been working on core health stuff and also the core stuff with Komodo itself, like the back end, kind of getting the code coverage up to cover all the weird intricacies that we sort of built on. But and then the ensemble team is led by Ollie, who is, I saw his camera earlier.
Yeah, sure, I'm on.
Okay, yeah, so they have an SBIR to pursue kind of core development and sort of education wing. And I think Ollie can explain better what they're bringing to the table as well from the commercial side.
Yeah, sure. Yeah, thanks, Asher. Again, hey, my name's Ollie. I've probably met one or two of you, but yeah, so on our side, we work with Asher in Predictive Science and CCMC, and are more looking at building out the kind of core infrastructure of Komodo with the help of Asher, as well as developing kind of a front end interface that kind of leans on the no code or low code movement. And that's part of the product demo that will show you, where you're able to drag and drop a series of model function outputs to easily render any model or function in a few seconds. So that's what we'll be looking at least for my part of the demo.
Yeah, so I think what we're going to start with is the sort of the introduction of the core technology and what the problem it's trying to solve, and then we'll sort of get onto the layers that built on top of that. So I think Darren is going to start with that.
Yeah, so actually, yeah, I guess we're a little more disorganized than I thought we were. So yeah, what I'm going to show you, so a lot of what we're trying to do is create this infrastructure that we can really connect and pull things together and pull things in, and we've done that in different ways. And the one, I guess I don't have the slides to show you. I'll just describe it in words, and we'll see how this goes. But a lot of what we've described is what we call commodifying models, okay, or commodifying a data source. And so what that really means is we're able to connect to some source of data, whether it's a model output, whether it's observational data, whether it's a purely made up function that you've created yourself, some analytics, whatever you want to connect it to. But in commodifying that, we're able to then pull that data source into Komodo and functionalize it. And we've not always communicated well what that really means, but really functionalizing something really means that you've got a function and you can work with that function as opposed to working with a set of data points or discrete data points. All model outputs and observations are really usually made up of discrete data points, but in functionalizing it, you can actually then display and zoom and analyze in a way that's far more powerful than just having the raw data sources. And so in functionalizing something, what you really have to do is have a good interpolator for that, which means you've got a set of data points, but you want to be able to know a continuous set of values along that line. You've got to know how to interpolate it. And for data sets that are complicated, the modeler is the expert that knows how to do that interpolation. And so providing that interpolation function is an important part of commodifying something. If your data source is pretty straightforward, if it's just a time series, things like that, the interpolator is a routine thing. You're just going to call a SciPy library and it's going to interpolate it for you. But we really want to focus on these being functional models. So you're actually looking at calling a function, and you can choose, a data range to plot and choose things and interpolate and grab things on the fly as if you were working with a function as opposed to working with a set of numbers, for example. And so we've really focused on that, and that sometimes has been a point of confusion for people. But if you have a complicated data set, you know what we're talking about, because interpolating is the name of the game. We've got a raw computational code, and you even do interpolations just to write it to a data file that can then be visualized and plotted. And so that interpolation is a crucial piece of it. The other parts of the commodification is really how we're handling, and we're doing this interconnection with PyHC, how we're defining our metadata standards and how we're making sure that packages are compatible and things like that. So all that commodification in the end is, if you've got a commodified model, there's a reader that can read in the data, provide a functional form or an interpolator for it, and then all the power of Komodo is available to you to make plots, to do interpolations, data model comparisons, all these powerful things that can be done once you've met that core threshold for an infrastructure to kind of start the project. And so I'm gonna show you a quick couple of things. I'm going to start with kind of a higher level and then jump into some actual Jupyter notebooks to kind of show examples of this. So let me go share the screen. Okay, so now I'm sharing a web demo that we've made that shows off what some of the things that Komodo, and this is hiding all the power of Komodo behind the scenes. And so this is now just a web page that I can go and I can pick a model. And these are looking at runs that are available at the CCMC, run on request runs that are just sitting there. And I can pick a model and I can create a plot for that model. And then this was a very, crude default value, but this is now using Plotly, and I can zoom in and I can look at values and things like that. So this one's not very exciting, but I can look at other figures that have been created from this model and look at something a little more exciting. And I'll look at this, which is 2 slices, which again gives you the power to zoom in, rotate, fly around, see what the value is at a given location, for example, and things like that. And so this is just using Plotly to kind of show off what we can do with it. If I look at another one, there's model output from the GitHub runs, and again I can go and look at plot values and look at plots that have been made for a variety of things. And so I can actually just go and look at this page. And that basically that stores all the set values that'll interact with Komodo in the back end to generate this figure. But if I actually go to the Jupyter notebook to kind of look at a similar thing, so these web pages are just a front end that runs the Jupyter notebook in the background. And if I look at a particular reader, so again, this is the GitHub model. And so we're just going to be, you know, importing our GitHub reader from Komodo, a few other just basic libraries we need to have. And I'm going to point it to a directory that I've got a bunch of GitHub results sitting at. And I'm going to say, hey, just grab the last file in this directory. And when I then say, okay, model equals, you know, GitHub of these variables, it's going to open that data file, pull out the timestamp, the raw data size, a bunch of metadata, look at how height, altitudes, things like that. And it's going to find all these variables packed into there. And so all of these variables have been read out from this model. And this model has then been commodified. So all these variables are now available as a function, not just a discrete set of points on whatever grid was in there. And so I can actually then probe and look at these at any given location. And there's different ways. Then I have a couple of examples of ways to interpolate. You can actually, you know, put the variable name in here or make the variable, the density variable as a passed in argument. And I can call my interpolator. And I've set up here a grid of just 4 different points in space. So this is basically a longitude, latitude, and altitude positions. I've just said, hey, these are the 4 points I want. Give me the values there of density. And so this is pulling out the metadata for what the units are, looking at what the values are at that location. But then I can make some really simple plots, and I can just say, hey, you know, I've got this. I'm going to say get plot for density at this altitude, make it a 2D altitude plot, give me this color scale example, and then I can get this plot and I can analyze it and look at it. And so these are straightforward things you can do within the notebook to make a variety of different plots, whether they're 2D or 3D. If you want an ISO surface, you can make an ISO surface of a given value that you can then look at and plot. And all these plots can be interacted with and customized greatly as well. So when you're in the notebook, obviously, I've just said, give me the default setting for this, but I can really customize a lot of things on this. One of the more interesting examples as well is looking at pulling things in from Happy. And so we've commodified the Happy client. So Happy has, again, a Python package that they've set, and we've put a Komodo wrapper around that. So again, I'm going to read my Happy reader in Komodo, point it at the server, point it at the variables I want, and it's going to go hit the data set. I didn't specify a start and stop time for this, and so it's just going to grab the last hour available, registering the variables, registering the units, a bunch of those things. And then I can just go say, hey, make a plot, show me in the GSE coordinate frame, you know, 1D position, scaling things by Earth radius. And so there's a plot of that last hour of data. And I can look at it in 3 dimensions, and I can plot it on an orbit and then color code it by altitude in kilometers or various things. And so those are all straightforward things you can do. And I can point it at CDAW as well. So all the stuff that's available on CDAW can be grabbed easily, pointed at the server, grab it, register it, and then it pulls in the data. And this first one's boring, it's just the positions, but then the next one I want to plot what the values are, and I can look at the magnetic field vector that's available in that plot there. And again, in interpolation, there's examples in our notebooks that we have online that you can look at for interpolation. And I want to show one other quick modification to this. So again, we've got a similar one. The runs on a request have satellite extractions, and so when you run a model at the CCMC, we fly satellites through that model, and so we have a GOES 11 fly through of a 3D MHD simulation, and we can extract that data and pull that in as well. And so these are now MHD quantities that we're able to plot and look at, and this is looking at just one particular component. But now I can go down here below and say, well, let's pull in that same data from CDAW, and I can then overlay a whole bunch of things and choose this. And so you actually see what I've done here, and if you look at the code, is I've kind of called our default, you know, run a request, show a BX plot, and I made a few plots. I grabbed a plot from the Happy stuff, and I'm just adding them together and then dumping the added together plot together in one image. So they're all in one scale. I can zoom them together. I can turn on and off variables and all this nice interaction that I can do looking at and analyzing these plots interactively and doing lots of analysis that you want to do with these things. And so now I can look at just the comparison between the modeled BZ and the observed BZ for these values. So so that's just a quick example of applying this to model outputs and what we can do with putting a web front end on things, but also putting giving you the access to the full notebooks, so you can do whatever analysis you want to do beyond this, and making things far more complicated. So
these are
questions
available to me to compute with?
Right. And so these are, again, this is available for you to work with. I'm pulling in the data just through the web access, but now the data is actually sitting in Python in the Jupyter notebook for you to do whatever you want with it, right? And so if you've got some other pipeline or analysis tools, this can then feed into that and do any further things you want to analyze these data.
So I've got a quick question here. So Darren, when you're showing these dots, I assume that's like where the measurements were taken, or where the model output is. Is the lines connecting those? Is that the functional? So like, let's say you have a output, at a 1 minute cadence. How do I know what the functional is if I want a 30-second?
Yeah, in this particular instance, I'm actually just showing the points are the actual data points, and the lines are just connecting those dots. In this particular example, I'm not taking advantage of the functional form in this particular one, because when you have the functional form, you can do more with it, but you can also just show the raw data. And so these actually are just the raw data points with a line just to make it easier on your eye.
Okay.
Yeah, and we sort of have a convention that you can do both by specifying the defaults of a function to define its default domain is returns the raw data. So if you want, so basically you can automatically generate a plot that gives you the raw data output. But if you want to look anywhere else within that domain, you can zoom in and you'll get interpolated data. But so to the end user, they're almost indistinguishable, but it lets you do kind of the best of both worlds, the data and the functional.
In this case, the function would just be linear interpolation, for example.
Yeah.
But it's up to the author of the.
Right, but I mean that's the typical thing you would do if you just wanted to do an FFT and you needed to fill in some points. You would just do linear interpolation over there.
Right, and that's the simplest. But anything more advanced is certainly possible to do, right?
Yeah, so I guess my question was like on those surface plots then that you were showing before, that's more the raw data then. So like if I zoomed in on that, how would I know what model resolution I guess I'm so like this kind of gets at the am I looking at a high resolution model output, or so 1 degree or maybe a 2 degree model output, and then is there scatter points or something to let me know where the model output actually was versus the real data? So I think you were kind of getting at that, Asher, that you can plot both still.
Right, and this particular slice is actually, I've chosen a 1 degree resolution to show this at.
And so that's what the model is output at, or not?
No, the model is not output at exactly one degree, right? This is using the interpolation to get you a quick, smooth figure, basically, right?
Yeah, and there are other, so Komodo's has a bunch of different types of plots that can also maybe provide more visual cues if you want to provide that level. So you could say show glyphs or something at the model resolution, and then, but it's sort of you would need a different function that Komodo understands how to plot to track that information. It's not exactly automatic in that regard, but partly because the issue that it's generally the case that people don't really want the raw data. They want to get the data at their favorite grid or at their timed cadence because they want to compare it with some other thing. And so, but you can always go back to the raw data under the hood. So I'm not sure if this might be a good time for me to show that kind of the intro.
Yeah, that'd be good.
Okay. So this will give you a little bit more context about Komodo itself. So from a kind of a bird's eye view, trying to hide the UI, it was always getting in the way. Okay, so this is sort of like, this is the introduction notebook if you were to go to the Komodo website, and just sort of showing you from a super high level just what Komodo is trying to do. Just so Darren's sort of showing you, like, here's some specific examples of things that we built with it, or that they've built at the CCMC. But this sort of emphasizes more since this is a Python audience, we don't usually show things at the code level, but I think you might be able to follow. So when you're registering a data source in Komodo, or a scientific resource, as we're calling them, you're using this dictionary sort of syntax to initialize the Komodo object. So it's a functional sort of approach, but we do have to use objects, obviously. So we have this Komodo thing, and you basically register functions into it. And these are just showing, simple things, but basically, you have f of x is x squared. And then if you want to evaluate that function at a given point, you just you treat it as though you would write it in mathematical terms, and as in use the call operator on that function. But what Komodo, once you've got things registered, it's like, well, you have these functions separately, but now Komodo understands function composition. So for example, if you register a new thing, in this case, f, and you say it's g of x, but x is a function of t, then the composition is sort of handled for you. So Komodo figures out through function inspection that f is actually a function of time, even though you wrote it this way, or a function of t, for example. And so when you evaluate functions, I mentioned you use a sort of dot notation, and you can grab the the doc strings are automatically generated for these types of functions, and then these things automatically work on NumPy arrays, so you can hand in a very large array, and Komodo can evaluate it very quickly. I think I need to actually go back and execute these. Here we go. So it's and so the reason for that is it'll use either NumPy or the numerical expressions library, which is faster than NumPy in a lot of cases. So that's for pure functions, and then it does unit conversion. So it basically, the way we treat units is that units are metadata attached to functions, and they're not embedded in the arrays or the data that's passed around from functions. So the reason for that is that so essentially what we're trying to do is eliminate the units from the right-hand side of the expression, if you will. So it sort of lets you validate the, so for instance, in this case, I have these two functions, mass and volume, and they were specified with kilograms and meters cubed. But if I want to, compute, so automatically, if you divide these two, then Komodo will be like, oh yeah, it's kilograms divided by meters cubed. But then if I want to specify my own units, I want this to be in grams per centimeter cubed, and I think like kilograms or heretical or something, then I can specify on the left-hand side what the units I want my new variable to have. And on the right-hand side, I just say use whatever variables are in that dictionary, and then Komodo figures out, oh, you need to divide by 1,000 if you actually want to do this. So this allows you to validate your expressions with like kind of back of the envelope kind of manner. And then it doesn't, what you have coming out of here, like Komodo doesn't necessarily care what the data types being passed in or out are. It'll just multiply and divide by these units that it automatically inserts. And we can talk more about unit unit stuff later, and how this differs from like AstroPy units. Yeah, so you can get metadata out of here. And then we have these kind of variable naming conventions. So if you use Greek variables in your expressions, then Komodo will render that as Greek. And it actually does LaTeX output for these things as well. And so, but since we're usually not dealing with just pure functions, we have this commodification process where basically we just have this commodified decorator that you slap on the top of your function, and then it basically adds the metadata necessary for Komodo to do the function composition and unit registration stuff. So so here's like a generic function that I'm just calling row. This can be anything. And I'm just registering it here. And because I named it row, it has this nice Greek symbol. And then on the right-hand side, it's just saying this lambda is sort of a placeholder for the actual Python function that is registered here. And so it's just a visual way to tell you that there's no closed form representation for this function, but you do have access to it. And then Komodo kind of carries on as normal. So once we have things in this manner, it turns out like a whole lot of problems in space weather are just function compositions, but they are function compositions, like coordinate transformations or data pipelining. You can sort of think about it as functions that talk to other functions. So once you get things into that format, then a lot of things become a lot easier, like plotting becomes easier. So we have we use function inspection to figure out what type of plot you're trying to generate. So based on the number of arguments and the shapes of those arguments. And so that's what this table is representing. And then we have like a visualization notebook that sort of demonstrates that. And then here I mentioned the LaTeX AI or API, Freudian slip there. So I mentioned that, so we have this commodification thing, and I said that there's basically, this function could be anything, including this function could be something that doesn't even live on the server, live on the client or in the notebook. So working with Ensemble, we've been building out this Komodo API, which basically lets the function and the data live on a server and allows you to access it in a way in a notebook without actually installing any of the readers or interpolators or anything yourself. And so in this example, I have 2 Docker containers that are running on my machine, and they're at localhost here. And this is one of them is a core held container. So when I just create this Komodo client, which is a subclass of Komodo, and it just accepts a single URL. And what spits out is it says, oh, I have all these registered variables. And now if I want to plot, so the magnetic field.
Lambda.
Yeah, so all the lambdas essentially live in the Docker container in this case. Is that what you asked, Aaron?
They're all the same function.
No, so lambda functions are kind of in the parlance of functional programming. They're sort of, you can think of them as placeholders for actual code. So I could have written out like the names of these functions, but they wouldn't tell you anything more than the fact that it's basically a black box. So you could think of it as black box of phi theta r. So that's what lambdas mean. It's the left-hand side that's important to the end user. So the left-hand side, we try to use the same symbols and notation that are in the literature. So depending on what field you're working in, you might have different names for different variables. But so yeah, pay attention to this side. This side just means, ignore what's going on the right-hand side. It's not important to you. It's Komodo can handle, is just trying to expose to you these variables as fields. So this, for example, is an isosurface of the radial component of the magnetic field. So if I set this to 0, you'll get.
Quick question back on the lambda thing.
Mm-hmm.
Would it be possible to have it replace that with more of like a documentation string or something about that variable rather than the generic
So
thing that actually.
if you want the documentation, you can do.
No, I mean, instead of the BR equals lambda, B phi equals lambda and everything, have something else useful there, because it does seem strange that they all map to the same symbol.
Yeah, so we have this the detail of you can call this detail method on any Komodo object, and it'll give you kind of more insight. And in this case, I'm not actually registering the units for these things, but the symbol on the right hand side, this is something that we could have written on the right, but it wouldn't say anything more than what's on the left.
Yeah, no, I'm saying like some kind of metadata phrase or something about that description.
Yeah, it's kind of a design decision, because it's not just like, in some cases you'll want to say in English what's going on the right hand side, but other times you have like expressions, and we're trying to emphasize the mathematical nature of what we're doing, and so we're kind of treating like Komodo doesn't really care what is in these functions, so we don't want to like mislead people that it actually knows what those English words mean, on the right hand side.
Well, but I'm just saying, for explanatory purposes, it's really conveying not much information, so you could replace it with something else that does convey more. That's all.
Could I chime in from an outside perspective? This is Matt Young.
Hey.
It's very common to write f of dependent variables to just indicate that something is a function of those, and I get the impression that that's all they're trying to convey. Is that right, Asher?
Yes.
I mean, and so in that case, it's just, lambda is in the place of the symbol f, because it's more appropriate here, because lambda is a way to represent an anonymous function in computing terms. And so that's the information that they're conveying. That's all they need to convey in this situation.
You said it much better than I usually do.
Yeah, it's an excellent statement of what it means. So it's an anonymous function, so it's not a closed form, so we don't know the function. It's not an x squared times y squared or whatever. And so it's just an unknown function, and
It's
the
not an
inside of a
assignment.
function is of course different for each variable
Mhm.
based on the data. But I think even the structure on the grid is very similar between all the variables. But yeah, so to really get the numerical data and stuff, you would
Yeah.
have to
Let's
call the function with default parameters, and then you get
It's not an assignment statement.
yeah.
Right. And let me just try to wrap up, because we want to get to the last demo. But I just want to show that we have we also register user. We're calling user models. So this API supports putting in so in this case I put John's name in here. And what comes out of here is his own kind of registered model that's sitting on the server. And so when he makes edits he can basically use the API to register new functions that are compositions of other functions on here. And this is his own personal URL now. So we're sort of using this to build up sort of a framework for letting people do kind of user-defined things. And then finally, I wanted to show the CNOFs instrument. So this is coming from, we commodified the PySat project. So we basically wrap all of the, a few of the PySat instruments. It should support all the PySat instruments, but I haven't tested all of them yet. But in this case, this is the CNOFs instrument on VEFI, or maybe I have the platform in the instrument switch. Jeff can correct me. But these are all the variables that are hosted there in that Docker container. And then when we plot, for example, the magnetic field northern component, we get this nice graph automatically generated. And this is using, I believe, the raw data. Yeah, it's the raw data, but it's just kind of at a lower cadence. And then if we want to register, say, the square of the magnetic field, we can just add up these components, and that gets added down here to the list or to the dictionary. And then we see that expression up here. So it's basically handled all of by containerizing PySat, we're able to sort of handle all of the installation issues of PySat, not issues, but the user doesn't have to actually install PySat to use PySat now. They just have it in a container, and that's serving the Komodo API, and you can then build your whole sort of graphical user interface around that. And then, so if you want to do like data model comparisons, now you have both the ability to access data, you can access models, and you can fly satellites through models with function composition. So yeah, but in the interest of time, we'll switch over to Ollie so he can show you.
Well, and we need a little bit of time also for Rebecca too. So.
Oh yes, okay. Yeah, I need to.
Sure, well, I'll go very quickly because Asher just kind of verbalized it. What I'll be sharing, but I'll make sure not to take up too much time. So can everyone see my screen?
Yes, looks good.
All right, great.
Yep.
So as Asher mentioned, one of the things that we've been building out really is the containerized infrastructure to deploy kind of commodified models and functions. And this has a few key advantages, one of which it kind of simplifies the process of running and creating these visualizations. So as Asher mentioned, we have first commodified and then containerized PySat and then also CoreHel. So you're able to easily just drag and drop a variety of these functional outputs in a matter of seconds, and then kind of do all of the things that you're able to do in a Jupyter notebook with the Plotly interface. And so again, this is just kind of the opportunity that Komodo provides is to kind of simplify the process of modeling all of these different functions. So this is just kind of a proof of concept prototype. In the future, we hope to bring many model outputs into the interface so that users can just drag and drop and then be able to create these visualizations. And then another area that we intend to develop is kind of a widget board so that, again, users are able to really easily kind of identify the right context for visualizing whatever it is that they choose. So it just takes a few seconds, and then you can see we have, you can add more plots, and then there is some widget kind of functionality, and then you can update it. And so all of this is running on an AWS infrastructure. And just again, kind of showing more downstream what Komodo is capable of. And the other big thing that we're really interested in is just simplifying the process of running these models so that users don't actually need to kind of set up the infrastructure to run these models. So one of the key kind of users we're interested in is new students and new folks who would be interested in learning about space weather. They might not know how to, they might not be the most savvy Python or Jupyter Notebook users. So this would be a great opportunity to simplify that process and kind of bring more folks into the space weather modeling visualization world. And then, as you can see, we also have a function editor. So I'm just going to run something pretty quick just to kind of show we also have the ability to do custom functions, register custom functions. And then in the future, we hope to be able to perform essentially function composition in this control panel so that you would be able to, in theory, combine any of these models or any of these variables and then do all of that within the function editor. So this function editor supports LaTeX as well as Python expression inputs. And then there are, of course, you have ability to upload raw data and then just define that variable and visualize it. So that is pretty much all what we've been working on. And really, as I mentioned, it's developing the ability to deploy these capabilities via AWS, via containerization, and of course, the API is a really key component. So that's more what we've been developing, and Yeah, also, I'll just pause there. Are there any questions before I hand it over to Rebecca? So you can see we just pulled these up. All right, so I will stop sharing. Again, if you have any questions, just reach out to me, and we can chat about kind of what we're showing. Asher, anything else you want to comment on this?
Well, you're applying for phase 2 to commodify all the
Yep.
things, right?
Yeah, so we've applied for phase 2 SBIR, and really, if we are lucky enough to get that award, we would significantly expand the kind and create like a library of functional outputs, as well as making this interface a lot stronger and kind of trying to essentially be the Tableau of space weather and create a really intuitive and useful interface for modelers. So that's what we hope we will get, but that's kind of where we are for right now. So I will stop sharing my screen. And then Rebecca, if you want to take over.
All right. All right. Let me share my screen. What I have been working on is getting Komodo to talk to Plasma Pi and PyHC. I'm just going to do this. And click all the buttons. Great. All right, here we go. So this one. All right, so I ran all this beforehand because it makes the fan turn on and the computer fan's a little loud. Okay, so I'm going to go quickly. So what I'm showing here is a little code block that demonstrates that you can commodify AstroPi quantities. I'm not going to dwell on this for long, but it's necessary because Plasma Pi expects inputs that are AstroPi quantities, or it converts your data to be an AstroPi quantity. So I need to be able to distinguish for you what's going on in which case. Okay, so what this does is I'm simply making 2 sample arrays, okay, making a few AstroPi quantities that have different units that I'm going to play with later for you. And then you can commodify these different AstroPi quantities by either pulling the value property of the AstroPi quantity, pulling that for the data, and then you can pull the units from the AstroPi quantity with this property here. And the OGIP is necessary, or the unit translation will not be nice to you. And then you can show one of them, or I can just show all of them, and it shows you the units properly. Okay, so you have the correct units that I assigned to the particular AstroPi quantities. Okay, so you can commodify AstroPi quantities quite easily using the properties that are inherent to those quantities. Okay, but everything else is run already. So I wrote a wrapper, and this is currently what it's called. The current version is on GitHub, but it's not installable. You just download and run it for now. I'll make it nicer later. But the basic things I want to demonstrate is that you can import whatever functions you want from the Plasma Pi library into a Komodo object in 2 different ways. One, either into a new Komodo object that has nothing else in it, or another way into a currently existing Komodo object with, say, your data in it that you want to manipulate through these functions. You can import either the functions you choose or all of the functions possible in the Plasma Pi library. I'll get to some of the exceptions later. 2 things that I had to make choices on for design or based on the possible input units for Plasma Pi, because as the others demonstrated, it's the units, the unit conversion is one of the powerful features of Komodo. So some of the Plasma Pi functions allow multiple input units. So I had to make a few design choices there. And also a few of them have options for multiple output units. Okay, so for the ones I'm choosing to show here, say for this one, the upper hybrid frequency in Plasma Pi is an example of one that has multiple output unit choices in the function. So I show that here, these 2, the omega UH1 and UH2. So what you'll see here is the same exact inputs. and I give two choices, one for an output in radian per second and one for an output in hertz. So I simply represent them as two different functions instead of in order for users to have access to both of the features. So two things you should notice here is that the name of the function is automatically chosen based on the Plasma Pi documentation. The name of the variables are also chosen in a similar manner, and the units of each variable, both input argument units and the output units of the function, are automatically determined from the Plasma Pi documentation. Okay. The items that are words like this ion underscore saturation current, that was the best guess it could get from the documentation. So as the Plasma Pi documentation matures and attaches more variable names or more symbolic representation of these things, then it will automatically update based on your particular Plasma Pi version. So here's an example where you can just add some data to a currently existing Komodo object, which has already been shown, and that new piece of data is just shown at the bottom here. So here's an example where you can, if you already have an existing Komodo object here, say Komodo underscore list from before, you can import whatever Plasma Pi object you want, even just one function, into the current Komodo object, and you just hand the function, this KPP list Plasma Pi function, hand it the Komodo object, and it hands it back to you with your new function attached. One thing to point out is that Fermi integral, the name of the function in documentation is integral, which Komodo and the attached dependencies interpret as an integral sign, which is unfortunate. So in this case, it's hard to know how to call the function, but you can use that detail feature here to see that the name is actually integral. And a couple features to note on the way for some details. Plasma Pi is built on a directory structure for their functions. They're in different categories. One way to find out where the function came from is to use the module property and the name property of that Komodo function, and it gives you the directory structure. You can also automatically, let me finish this up. You can also automatically look at the Plasma Pi documentation just by looking at this doc property of the function. And this pprint is just a way to print it in a nice way. That's one of those Python things. So I wanted to show the units. Oh, and we automatically include the Plasma Pi citation so that everybody knows where this came from and the correct version. All right, so the difference between handling Plasma Pi units and between Plasma Pi handling the unit conversion and Komodo handling the unit conversion is a little tricky, but with not much time left, I'm simply going to say that they are both equivalent. So if you input, say, another Komodo object that was, whether it was built on a number or an Astral Pi quantity, you get not only the correct numbers out, but you get the correct units. And if so I'll tell you that this B1 and B2 had different units. This one had Tesla, which is the standard input unit. This one was nanotesla. Notice the powers of 10 were automatically converted in this case by Plasma Pi, because this is an Astral Pi quantity. In the second case here, Komodo is handling the unit conversion, which you see in the function representation here. And what happens is the Komodo function only hands the data off to the Plasma Pi function, and you get the typical warning from Plasma Pi, but you also get the same exact numbers. So in the second case, Komodo has handled the unit conversion as compared to the first case where Plasma Pi did. So either way is possible. You can use the function composition to make different plots, whether and it's a lot less effort than before, as others have shown. You get the proper errors when you, say, hand number density with the wrong units to the function. It errors also from the Plasma Pi side, and it errors from the Komodo side, depending upon which way you approach this. You can pull all the Plasma Pi objects with a few exceptions. So the exceptions you see are the Plasma Pi functions that either require or result in, say, tensors or class objects or such things like the characteristic property. Those are things that the wrapper can't handle. So there's a couple exceptions here, but you can see that those are exceptions to the rule. So lots of functions available for whatever you want to deal with. And that's what I have here. Any questions on the AstroPi or Plasma Pi interface here?
Do I have to set up all these functions and things? If I've got a set of quantities and I want to know what the upper hybrid frequency is associated with this time series.
Okay, so you want to input AstroPi quantities into Plasma Pi function. Is that what you're saying?
Yeah, I guess.
Okay.
I'm naively a user, and I've got
Okay.
things that I can read with Happy or whatever from some database, and I want to use Plasma Pi to calculate various frequencies and lengths associated with quantities I have.
Okay. Well, your first step will be to pull in that function from Plasma Pi in a statement like this. If you don't already have a Komodo object, you simply just don't include this second option, and it pulls that function into a new Komodo object. And from there, if you already have your data in an AstroPi quantity, you simply do this.
None of
This
that
line right here. So this is an AstroPi quantity. Watch what happens if I do this.
Even at the first step, none of that intuitive. I don't
So-
approach and say I'm going to write this
Well,
function.
and Aaron, this is like a use case, right? So you have a particular use case, and if you could formulate that question for us, we'll give you a formula of how to meet that use case. But yes, what you're asking is all very possible to do. It might be a little complicated to look at, but we can create a document that meets that use case or request.
The thing that I'm complaining
you happy
about
to-
is that it might be a little complicated to look at.
Yeah,
No,
so the
so
happy-
the
there's a
functions,
happy-
Look at, nobody's ever going to use it.
There's a
so if
happy
you have
modified.
if you
Sorry,
have
I'll let-
data in an AstroPi quantity, you can simply, once you have the Plasma Pi function pulled in with a statement like this, okay, after this Komodo wrapper has been imported, just this statement and then this statement, you can simply put your AstroPi quantity in. So that would simply be one more statement. Let me find it. This piece right here, where this B2 underscore AQ is just your AstroPi quantity that you've made. This piece right here simply tacks on this unit. You don't have to include this piece. This is what your statement would be. Did that answer your question?
It's telling me that it's all very, it's simple in principle. I'm not saying it isn't clean and nice in many ways, but in terms of a user just coming in, a typical person, scientist who isn't necessarily up on all, whether they have AstroPi or Plasma Pi or whatever units and all that, or that doesn't mean anything to them. They just want to say, okay, I want the upper hybrid frequency associated with this set of data.
Oh, then that's a different question. Then what you would do, I showed two options here. You can either, once you have the Plasma Pi function pulled into a Komodo object, like I showed a couple times already, you simply plug in your data. Where was that option?
It's just that it's the interface. The interface is too hard.
Okay.
People
the
are
happy-
quick.
Sorry, I just want to say that we commodified the happy interface so that with one line, you should be able to pull in all of the happy stuff. And then she's showing that with the second line, you should be able to register any Plasma Pi function like hybrid frequency. And so then with your third line, that's when you would actually write the composition to compose the happy data with the thing. So it might be 3 lines, but it used to be 1,000 lines. Yeah, so it's
Really going in the right
we're trying to get it down to one line maybe, but
Right.
that requires
going in the
a
right
GUI.
direction. It's just I'm trying to be a typical person coming in trying to use this, and in order to get utility across the community, it has to be really simple.
Right, and once you have the Plasma Pi function imported and your data existing with the happy interface, you can pull even if you're just uploading data from a file that you have from your computer or a file from online somewhere, you can pull in your data with a statement similar to this, where this B1 is your NumPy array of the data. You put in your units. You don't have to even include argument units. You can use the functional composition portion of Komodo here. So I'm saying I want this EB function that I have pulled in from Plasma Pi.
These are not concepts that are typical.
Hey, but we're
is going to be aware of in any level.
Well, that's
Right.
why you read examples.
And we're creating multiple layers of this. I mean, Komodo, we're designing it to be really a powerful tool. And if there's subsets of it that would be useful, then we're doing, you know, a web front end is simpler, you know, all these graphical interfaces, just one little step more to do some things. But if you really want to get into do really powerful advanced things, we're showing you the raw Python in this case, given this audience. But we're trying to create a whole spectrum of accessibility points, right? And what we're showing today is a lot more of the advanced stuff, but we're trying to create a whole spectrum of ways to access what Komodo could do.
Yeah, it sounds good. I like the direction. I was just trying to be the.
Well, I think it's an important point, Aaron, which is that, you know, across the board, you know, as Darren said, we are trying to have accessibility points for all types of users, but all types of users still need to be educated, and that kind of educational content should be simple and easy to onboard across the board for any type of user, expert or beginner. So yeah, I think it's still important, and it's still something we need to constantly be building on, is how to educate and also communicate the value in going through a commodification process. So I think it's an important point, and something we constantly need to be working on improving to help kind of get this up and kind of at a production level for a variety of users.
Yeah, and I just wanted to say you know, we're building on the work of this community, like, and I'm really proud to be like really glad to be able to finally show it to all of you. So I'd really like to, if we get any feedback from Nick or Russell or Jeff or, you know, anybody who's we actually just showed some of your stuff, and we want to know, like, what do you think about this?
Yeah, it's really cool. Great to hear that you're working on commodifying Plasma Pi. I think it'd be good to talk more, because there might be some things that we can do that would help with like the rendering of symbols, like maybe having specifying standard symbols for different things. And also, if you have like feedback on ways that the interface for Plasma Pi could be improved too, we'd be very interested in hearing that. So yeah, this is cool.
Sweet.
Yeah, and we're obviously planning to be involved in the PyHC spring meeting, and hopefully we'll get a lot more discussions. We can get into more detail or higher level, however people are interested there.
I saw Russell briefly, but I see Jeff is still here.
Yeah, I'm still here actually. Hey, Asher, I was just about to comment. So yeah, I thought it was really cool. I mean, that the drag and drop interface to visualize the data and the coupling and all that is, it's exciting. I think it's really cool. So yeah, I'm just excited to see what y'all keep doing with it and get to play with it.
What do you think is
impressive
missing from the? I mean, like I mean, other than Aaron's point that it's too complicated, but
that's only for those who don't know Python, to be honest, right? I think that's his main complaint.
It's this is a longer discussion. It's not just you don't know Python. It's I want a little function that says ion inertial length of quantities. I don't want to set up things and worry about anyway. It's a long-term discussion. I like the direction. I think Komodo's great. I'm not really complaining. I'm just trying to, because so many things hit the ground dead because they don't take into account the audience in a deep enough way. We've had numerous things come through CCMC, numerous different visualization schemes and whatnot. The only one that's survived is the IDL thing, I think, that doesn't do a very pretty job, but it gets the job done. So anyway, that's just warnings.
Russell here, if I could just also just know a little bit about my experience with Komodo. I think Komodo is really general. So I think I kind of struggled to really understand Komodo. And each time I'm on, I see a talk or anything like that, I get a bit further along. So, you know, each time it's getting better. You know, I think that becomes a challenge if you have a tool that can do a lot of things in a generalized way to get it, explain it in a simple way. But, you know, with the more demonstrations and stuff like that, it becomes, you know, each time it gets better for me, I think. So I don't have a solution generally to that problem, but, you know, I think it's because Komodo can do a lot that it becomes tough to digest at any one setting. And I haven't myself personally done much with Komodo, but whenever you show me stuff, Asher, it's like, hey, that's, you know, it's good stuff. So
is there a sandbox
yeah,
we can play in? Is there a set of things we can download and use?
Yeah, so we have the there's 3 places. There's like this is the Komodo website that's hosted at the CCMC, which gets periodically pushed through the gauntlet of security measures going on there. But the freshest or the most up-to-date code base is from my personal Git repo, so that gets merged into the official Komodo NASA Git repo. And then so that has most of the bug fixes that we'll get there. If you pip install Komodo, you'll get a kind of an old version that doesn't have most of the features that we showed today. Some of the things that Ensemble worked on in the last 6 months that are not in there yet are the function composition stuff having to do with functions that take units and give units. And also the whole API and all that stuff. So we need to update those things. So there's a bunch of notebooks on the Git repo. So if you Google Git Komodo, you'll find it there. I think someone should have a link in the chat. But yeah, besides that, the Docker containers, I've just kind of started working on Dask integration with Komodo. So being able to do farm some of this analysis or interpolation heavy lifting off to a cluster of Docker containers through Dask is basically going to help us with improving the speed and reliability. So if you're doing like a very long study that you have so much data that it doesn't actually fit in memory on your machine, that's where you would use Dask. Yeah, so that's another thing. And it's sort of like, we're sort of learning the formula is that you take whatever the thing is that you're trying to, either it's an object-oriented API or it's some giant brick of data, and you try to create a functional form of it, and that requires learning in detail all of the intricacies of those APIs. And so that's the labor-intensive part, and so that's what we need the most help on is that as we go after these different things. And we really need people who understand. Like, it would be easier if other people commodified everything for us, but I think something that, you know, with the ability to have funding from through the SBIR, but also through CCMC, and then predictive science is sort of more focused on the solar end of things. So the next thing that we're looking at PSI is SunPy, and trying to get sort of how to represent images in a functional manner so that you can do things like so the coordinate transformations and stuff, which SunPy does very well, but doing it in a way that it exposes it to other types of transformations and fits in with the rest of the pipeline. That's something that I'll be working on personally.
Hey,
so,
Asher.
Go ahead.
Just a note on that. So been in close communication with Anaconda on X-Array and Dask and the issues with world coordinate systems. They are currently soliciting information from communities so they know how to extend Dask X-Array so it works properly with world coordinate systems. I've been on a few email chains with folks like Jack Ireland and Paul. People develop SunPy. So I encourage you to reach out to those folks. We unfortunately were not selected for our SBIR and would have handled that ticket right there and then for dealing with that. So, but since all of the stuff is WCS, recognize that they are looking out for that and using something like ND-Cube while it serves a purpose. It really should be taken to X-Array and Dask directly.
Yeah, I often work in a hole and I forget about where I should really reach out to people who are already solving a lot of these problems for me. But that's always great to hear that it's like, oh, here's another 40 hours I don't have to spend on something.
Hopefully. Right. I think it's just the sharing of information right now, and yeah, who wants to line up and tackle it. Unfortunately, we don't have the resources to do it, but.
Hey guys, this has been really interesting discussion. I unfortunately have to hop off to another meeting, which means I need to stop recording, and we should probably be wrapping this up anyway because we've gone 15 minutes over. But thank you so much, everyone, for presenting and the awesome discussion. Maybe we should schedule another Komodo chat session in a future Telecon. I know, though, that you all will be presenting some tutorials at our spring meeting, so maybe we'll have some time then too. Yeah.
Cool. Thanks, everyone. Really honored to be here today. So
yeah, it looks really cool.
Thank you, Asher. It's good stuff.
Thanks so much.
Yeah, great
everyone.
stuff.
This is great.
Hey, Aaron,
Appreciate
are you
it,
able
everyone.
to stay on here? Take care, guys.
Stay on, yeah.
All right.